Hello and welcome to this physics video on internal combustion engines. I've been following the train of topics in Young and Freedman's University Physics. We're in chapter 20 on the second law of thermodynamics, and this video is on internal combustion engines. The previous section, and there's a video out there for this, is on heat engines. Heat engines is a phrase we use for engines that convert heat into work. And the internal combustion engine in your typical car is a heat engine. And so we want to explore that a little bit. Of course, the automobile has transformed the world. It's also probably polluted the world extensively as well and continues to do so. So we are moving toward electric vehicles and other kinds of renewable energies. However, an oldie but a goodie is the internal combustion engine. And the way the internal combustion engine works, basically, it is a heat engine. So it converts heat into work, not perfectly. That doesn't exist in the real world. We have idealized models, but in the real world, there is a great loss, incredible loss of heat. The typical, as we'll see in a second, the typical efficiency of a car engine is something like 36%. That means we're losing like 64% of the heat is lost, which is not a very good ratio. But anyway, an internal combustion engine in a car is a heat engine that converts heat into work. A heat engine has a working substance, so like water or something like that. The working substance for your typical internal combustion engine is a mixture of air and gasoline vapor. So it uses that substance as the vehicle of heat that converts the heat into the work that makes your wheels turn and you go places. We can consider this cycle a cyclic process. A cyclic process is one that pretty much repeats the same process over and over again. Now, technically, it doesn't use the same air vapor mix every time, right? You have to keep putting gas in your car, unfortunately. But because it's pretty much the same kind of a water gas vapor, not water, air gas vapor mix each time, we can, for all intents and purposes, call it a cyclic process. Now, the way the typical internal combustion engine works is we start off with an intake stroke. So you've got these cylinders, right? The more cylinders in your car, the more power you have. We used to have eight V8s, with that V. They were in the shape of a V, so you had pistons on each side, going back and forth. Um, or V6. Then you have the 4-cylinder engine, which doesn't have as much power, but doesn't use as much gas either. So you have within each cylinder you have a piston which goes up and down, and you have these. You may have these next to each other, and they're connected to what's called a crankshaft. And so when this one goes down, they're connected to the crankshaft in a way that when this one makes it go down, it turns the crankshaft. And then when this one goes down, it turns the crankshaft. And so the up and down movement makes the crankshaft go round and round, which is what makes your vehicle go, forward. How you get a circular motion out of an up and down motion. In each cylinder, you have a piston. And so they're kind of it's a 4-stroke cycle. So the intake stroke, the piston goes down, and you have a volume increase, and there is, and I guess let me try to reverse the way so you see it correctly. So you've got these two valves. So the intake valve, it opens up and lets the air gas vapor mixture in, and it does that during the intake stroke. That's when the piston goes down, and that's when the vapor comes in. Then you have a compression stroke, which is, and again, it's doing this because of inertia, right? You need some kind of a starter to get the thing going, but once it's going, it perpetuates itself. And so intake and then compression, we don't have ignition yet. The piston goes up. This is an adiabatic compression. No heat has been added during this point. And so then right when it's almost to the top, you have a spark plug that goes psst, and that lights the fuel. And when the fuel is lighted, you get another stroke, the power stroke. We got the power, you know, and the piston goes down. Um, and so this is what perpetuates the cycle. And then again, following the same inertia, it then goes back up, and the other valve opens, and the exhaust fumes go out of your muffler and exhaust pipe. Okay, so this is the four-stroke cycle of an internal combustion engine, and I've been talking about something called the AutoCycle. But anyway, this is the AutoCycle. So we have intake, we have compression, we have ignition, we have power, and then we have exhaust, and then it all starts all over again. Okay, that's the way an internal combustion works. Now, I just mentioned that this cycle in physics is called the Otto cycle, not the auto, as in drive auto, but the Otto cycle. Okay, so we start at point A. At point A, you have a certain expanded volume. Now R is called. I have it on the next slide. Let's go ahead and no, where is it? There. R is the compression ratio. It tells you how many times as big the volume gets. So typical for a car would be an 8 to 10. So in your typical stroke, the volume in a cylinder is going to expand 8 to 10 times what it was at the start of the stroke. Okay, so RV is not an RV you drive, but R is the ratio of how many times the volume increases in a typical stroke. Okay, so we start at point A. So we're starting out with the intake stroke already happened, and so then we have the compression stroke, which changes the volume from RV to V. From RV to V. It's a decreasing of the volume. This is an adiabatic process, which means there's no heat added. This is the compression stroke. Okay, as we go from open to or maximum to minimum, something like that, from big to little. And so we've gone from this volume to this volume, has been a little bit of an increase in pressure. Now, in the AutoCycle, when you go from point B in the process to point C in the process, this is where the spark plug ignites, and that adds heat, QH, our old friend QH, right? So heat is added into the system here by the ignition of the spark plug. That causes the power stroke. Bam, right? Okay. So at that point, we go from the minimum volume again to this large volume. So there is an increase in volume. It's another adiabatic process because no heat is added during this power stroke. And the pressure goes down because we've increased the volume, Boyle's law. And then this is where the exhaust is released and so forth, and the heat is lost. So we lose this amount of heat here. And then the cycle starts all over again. All right? So the efficiency of an AutoCycle. As I said, it's not very good. But let's go ahead, and this is the equation. This is what you need to know. The equation for the efficiency of an AutoCycle is 1 minus 1 over R to the gamma minus 1. Now you remember that R is the compression ratio. That's how many times the initial volume the stroke goes. And then gamma, you'll remember, is the ratio of the molar heat capacities, Cp over Cv. So you've got the molar heat capacity at constant pressure divided by the molar heat capacity at constant volume. Now for air, that ratio is about 1.4. This is from previous sections. Okay, so this is what you need to know. This is the formula right here. The efficiency of an AutoCycle equals 1 minus 1 over the compression ratio to the gamma minus 1. Okay, there you have it. Now, for those of you who want to know how to derive this, Young and Freedman tell you how to derive it. Again, you really need to know, this is what you need to know, but let me go ahead and go through the process of deriving this a la Young and Freedman. So QH, QC, our old friends. This is the heat at the beginning, the heat added at the beginning, and QC is the heat that remains after it's all over. And the difference between these two, you'll know, is the work done. So Q equals NC delta V delta T, right? NC delta T. CV is the molar heat capacity at constant volume, right? What is this TC and TB, TA, TD? Well, if we go back to here, so QH, this is the temperature at C minus the temperature at B, right? Or the temperature at A minus the temperature at D. Those are the final states, right? So this gives you delta T for the QH part, and this gives you the delta T for the QC part, the cold part, the hot and the cold part. Okay, QH is always going to be positive. QC is going to be negative because it's the heat that's lost, as it were. Okay, so now we remember from previous sections that the overall efficiency equals the QH plus the QC, which is negative, right, divided by QH. So we can plug and play, right? We can plug these two, plug this in for QH, plug this in for QC, plug this in for QH, right? You'll notice that the NCVs are going to all cancel, and so we end up with this. When we plug this into there, this is what we end up with. All right. Now, so let's go from there. Now, you'll remember from chapter 19 that TV to the gamma minus 1 is proportional to the next one, TV at a different spot. At one spot, now this is for an ideal gas. This was for ideal gases and adiabatic processes for ideal gases. And so what we realize here is that we're going to get a value for this idealized formula that is much different from the real value, because we don't use ideal gases in these sorts of things. But let's go ahead, and it gives us something to work with. So what I'm going to do is I can solve for TB in relation to this, and then I didn't put it here, but you can do the same TC and TD. It works for that too. And so then with a bunch of substitution, I've already mentioned that R is the compression ratio. So if I do a bunch of substitution, I get this mess where I basically plugged in for TC and I plugged in for TB from this formula. And I've got a big mess here. Now, if you want to look at the book, he actually gives more steps, but I was running out of space. So you can see that if I take the first part and the second part, right? I'm sorry, let me put it this way. So if I take this part and then add it to this part, then I get this over this, which is 1. And I'm left with this over this, which if I factor out a TD and a TA, I can cancel out that part. And I'm left with a minus sign, because I got to flip the order of these, and then I'm left with R to the gamma minus 1. So that's how we derived this here. That's where that came from. Okay, again, the main thing is to know this formula. You don't have to necessarily know the derivation, although you should know this. Okay, so some typical specs for a internal combustion engine. So for automobile engines, R, that is the compression ratio, is usually 8 to 10. That means you get about 8 times as much expansion after the ignition, as the initial volume. Okay, so that's a typical spec. Now, if it were idealized, again, it's not idealized because we're not talking about ideal gases. You've got friction, you've got heat loss to the cylinder, you've got turbulence, but if we had an idealized situation with an R of 8, compression ratio of 8, and a gamma of 1.4, which is normal for air, we would have a 56 efficiency, which is not very good. We're talking about even in the best case scenario, we would be losing about 44% of our heat. By the way, knocking, if you have an engine knock, that means that you're having detonation of the fuel before the ignition, before the spark plug. And a lot of times that'll happen if you have an R that's bigger than, say, 8 to 10. You can address that with high octane gas. High octane gas can ignite at the right time and have an R of 10 to 13. And the bigger the R, the more efficiency you can get if it ignites at the right time. Now, as I was saying, the average efficiency for cars, I think I might have said 36%. The average efficiency for cars is around 35%. That means that you're losing about 65% of your heat is not being converted into work. Oh, by the way, I don't think I mentioned that the area under the curve is the work. This is the amount of work that's done, the area under the curve, as you know from integral calculus. Okay, so that's basically the Otto cycle and the typical internal combustion engine. I want to finish this video with the diesel cycle, which is also treated in this section in Young and Freedman. So you'll notice the main difference is instead of having the heat added at a constant volume, the ignition in a diesel cycle takes place as the piston is expanding. So there's no spark plug in a diesel engine. A diesel engine uses the pressure to create the increase in temperature and thus the combustion. So instead of it being a vertical side to the cycle, it's a horizontal side. So instead of it being a pressure increase and a spark, it automatically ignites during the expansion of the volume. Okay, and of course, diesel fuel is a different kind of fuel. So with the diesel, and this is a much more carefully controlled kind of situation, which requires more, diesel engines require more maintenance than your kind of Cro-Magnon internal combustion engine. So again, let's say we start at A. We have the adiabatic process again of the compression stroke. By the way, the fact that this is steeper, don't read much into that because this is me drawing it. It's a little exaggerated. I do actually think that it is a little steeper in the diesel cycle than the Otto cycle. But anyway, so we have this compression stroke where the piston goes up, right, and the volume goes down, and the pressure goes up. But with the diesel engine, there's no spark, but it's as it then expands a little bit, it ignites, and then of course when it ignites, you get the real expansion. So you get a little bit of expansion as it ignites on its own, and then you get the real big expansion of volume with the power stroke, and of course constant pressure, but here the pressure decreases with the power stroke. And then again we have the loss, the exhaust of the fumes and the loss of heat, and then it starts all over again, and the area under the curve is the amount of work done. So the difference between the Otto cycle and the diesel cycle is again that you don't have an ignition with spark plug, you have an ignition as the volume expands a little of its own. The efficiency in this case for a diesel engine, a value of about 15 to 20 is typical, so you have much more expansion of the cylinder, which leads to greater efficiency, right? And so the efficiency of a typical diesel engine is much better, somewhere around 65 to 70%, much more efficient use of the fuel. So this has been the internal combustion engine from Young and Freedman's University Physics.